that, but sometimes I forget to record it, and so if you look in the other class, you might catch that. But did everybody get the leveling effect? Is that okay? And so when we look at this, the strong acids, how many strong acids have you guys memorized from? 7. Are there 7? Only 7? Are there more? Yeah, there are a lot more. And so all of them would be the same. So if you have a diprotic acid like H2SO4 that's a little different, the diprotic acid is going to yield a little bit more hydronium, making it a little stronger.
So, as a general question, if you were to ask us, how would you make silver nitrate? Like, I'm trying to understand.
Okay.
You're teaching more of like a theory base, so you want us to see the whole forest, right, instead of just one tree.
No, no. This example was this. I'm not asking you how would you create this. This is actually pretty difficult to create. And so how would you create that? Well, one way you could try to create it is just by doing a double replacement. This is the first reaction I thought of when I was doing this. But unfortunately, this reaction won't work because there is no precipitate, no driving force, no nothing. And so I'm stuck. Silver chloride happens to be insoluble, so you can't dissolve it in water. If you dissolve it in water, then maybe you can get it to react. And so now I'm stuck. How else can I dissolve it? And so this is where I ended. In my quest to form silver nitrate solid, I got this far, and that was it. That was it. But the problem with that was this. You know, I was focused on, there's no reaction. If there's no reaction, there's no reaction. There's no driving force, right? I am stuck. There's nothing I can do. I saw no potential way out of it. But it turns out that I wasn't really stuck because the way I was thinking is, I was thinking these driving forces work for everything, under all conditions. But what I didn't realize is that if you change the conditions, that can change what you get. And so let me tell you how to form silver nitrate from silver chloride. And so obviously there's no reaction here because there's no driving force, right? But what they didn't teach me, and I didn't learn myself, was this. Go back. They didn't teach me that altering the conditions can have an extreme effect on the outcome. So for example, here I would have automatically expected to precipitate. And so if there was no precipitate, then I'd think there's something wrong. Maybe I don't have silver nitrate in HCl, because silver nitrate in HCl makes the precipitate of silver chloride, right? And if I don't get a precipitate, I would have been stumped. I would have thought, wow, I'm not getting a precipitate, why? Something must be wrong. Well, the same thing here. The way to do this is this. If you have silver chloride and nitric acid, under these standard thermodynamic conditions, you get no reaction, as we just went through here. But if you alter the conditions, that is, let's say we don't use a standard concentration of HNO3. What if we use a high concentration of HNO3? So rather than using 1 molar HNO3, we use 16 molar HNO3, number one. Number two, what if we don't do it at room temperature? What if we elevate the temperature? The temperature is not part of this. You know, you can do it at any temperature and still be under standard thermodynamic conditions. But that's something I didn't think about. And so it turns out the way to get silver chloride to react with nitric acid is by reacting with hot concentrated nitric acid. And when you react silver chloride with hot concentrated nitric acid, one of the products is silver nitrate plus other stuff. You know? And so actually there's more steps to it. And this is not entirely correct. There are other products that are formed here as well, which I didn't write in here. But the problem is I was locked into this box of thinking that this is the way it is, in which I didn't really see the whole forest. You know, I was just focused on one set of conditions, and that's all I knew. was this one set of conditions. But when you open it up, there are many conditions and many variables, which makes chemistry quite a challenge, because once you start varying all these conditions, then you don't know what the product is going to be necessarily, right? And so what we have to do is we have to restrict ourselves to this. If we didn't do this here, then it would just go crazy, you know, as far as making reactions. It would be terribly difficult to predict, right? Because let's say I use 16 molar here, but what would happen if I use 6 molar? Would 6 molar have done it? Would it have been enough? Would 10 molar? Would 12 molar? Tell me where that cutoff is. Because 1 molar certainly wasn't enough. You know, that type of stuff, yes, you should be able to calculate that theoretically, but that's way too hard. And so this is why, did I tell you about the 1,000 reaction reactors that they have? A lot of chemistry is very difficult to predict theoretically, because there are too many variables that go into it, and there are too many assumptions you have to make in order to solve the math. And so a lot of chemistry, what's done is you want to find the best catalyst, you know. You're looking for the best catalyst to make hydrogen gas, or you're looking for the best catalyst to clean up the pollutants in automobile exhaust, right? How do you do that? Well, it would be great to do it all on the computer, figure out the exact composition of catalyst or alloy that you need, and use that. Well, that's too difficult. So what they do is they make microreactors. A microreactor this big can do 1,000 different formulations. And so you make 1,000 different combinations and then test each one of those combinations or compositions to see which one's the most effective. Right? And so that's the brute force. That's the, well, for us, you know, that's too much. There's too many variables, so we try to keep the variables simple. But the danger of keeping the variables simple is we miss the whole force. But this is the only thing we can do to keep this manageable. And so we're just going to concentrate under standard thermodynamic conditions at about room temperature. Does that make sense? Once you start varying that, then we got to compensate. And so this is why I'm saying this is a basic assumption, because things can change. Even here, you know, lead 2 nitrate plus sodium hydroxide. This is a reaction in Chem 1A. This is a really interesting one, because when you take lead 2 nitrate plus sodium hydroxide, it's a standard double replacement. We form a white precipitate of lead 2 hydroxide, and sodium nitrate is a clear, colorless liquid or solution. But what happens is, if you keep adding sodium hydroxide, the white precipitate disappears. And so you form the precipitate, you keep adding hydroxide, you expect to form more precipitate, and the precipitate just vanishes. It vanishes because another reaction takes place, and this other reaction is when you add excess sodium hydroxide, you form this. This is called trihydroxyplumbate ion, plumbate 2 ion. And we're going to talk about these strange looking ions. It's Pb with 3 hydroxides and a negative charge in chapter 24 when we get to complexes. This is called a complex anion. And so there are side reactions that might take place that, you know, you're focusing on double replacement. You aren't considering redox. This is not a redox, but you aren't considering acid base. This is an acid base. This is what we call a Lewis acid base type reaction. And so we got to look at all types of potential reactions there. Okay, the other thing is, even though we might predict it correctly, we're going from less stable to more stable. That's a thermodynamic driving force. We want to go from high energy to low energy, right? That's what nature tends to do. Still, nothing might happen. So when we compare diamond versus graphite, which one's more stable? Diamond or graphite? Graphite's more stable than diamond. Diamond's unstable, graphite's stable. So diamond should eventually decompose into graphite. But if you're going to wait for diamonds to decompose, you're going to be waiting many, many lifetimes, because it's just not going to happen. The decomposition of diamond to graphite is just too slow. It's so slow that we call diamond metastable. Metastable means it's thermodynamically unstable, that is, it should decompose, but it doesn't, because that process is too slow kinetically. This is what we call kinetics here, the speed of the reaction. There are lots of examples of metastable mixtures. If I fill this room up with methane, you know, here, we know that methane and oxygen, is that a stable mixture or unstable mixture? Methane and oxygen. Stable mixture or unstable mixture? Well, it's always relative to something. So if I take methane and oxygen, what it can form is CO2 and water. What's a more stable mixture, CO2 and water or methane and oxygen? Which side of the equation is more stable? This side is more stable, therefore there's a driving force, right? And so the methane and oxygen should combust and form CO2 and water. Is that what you see? If I fill this room up with methane, do you see combustion occurring? No, but I know I don't want to do this because there's going to be potential for explosion, right? This is another example of a metastable mixture, but this is less stable. All this requires is a spark or a hot surface. If I just add some heat to it, it'll start to combust or explode. And so I got to be careful. But at room temperature, it's a very slow reaction, so I don't worry about a fire here because it's metastable. I know, and I know I'm safe as long as there's no heat source or flame source or spark source to ignite it. And so even though, okay, when I mix, there's a great driving force here because methane and oxygen versus CO2 and water, these are gases. Sometimes I leave the states off. But if I leave the states off, the states are going to be left off for aqueous. And so here, if it's gas, liquid, or solid, I better write the states in. So gas, gas, gas. Here, there's a great driving force because a mixture of CO2 and water is much more stable than methane. This is not methane. Methane is, sorry, 4 oxygens here. I mean, 4 hydrogens there. Okay, so these are little caveats, you know, when we're predicting reactions, you know, not all the reactions are going to be predicted correctly, but what the advantage is this gives us a very good starting point, right? A very good understanding of chemical properties. It's the same thing. We need to understand, you know, what's stronger, dispersion forces or dipole? You know, we need some kind of reference points in order to be able to understand it. Well, this is how we're going to generate reference points to better understand chemical properties. And so we're going to see a whole bunch and memorize some stuff, and we should be okay, or better off understanding these chemical reactions. All right, let's look at the first type of a chemical reaction, metathesis. That's what we'll spend the rest of the day on. Metathesis, these are typically double replacement reactions, but they don't all fit the double replacement format, AB plus CD. So that's why I don't call it double replacement, I just call it metathesis. And the goal in metathesis is exactly the same as the goal in double replacement. We try to switch ion partners to find favorable combinations. And so metathesis are just finding favorable ion combinations. Well, how do we know when an ion combination is favorable? Well, when an ion combination is favorable, it forms stable products. Stable products would be like precipitates, gas, stronger acids to weaker acids. Those would be stable. But it's not always ion combinations we're looking at as well. Sometimes there could be molecular compounds like this. And so let me just take a brief tangent and talk about ammonia. Because when we're thinking about ionic compounds, AB plus CD, you know, ammonia doesn't fit in there because ammonia is a molecular compound. But we have to realize something about ammonia. Ammonia is before I switch to ammonia, let me ask you one more thing about the leveling effect. The leveling effect occurs for strong acids, but what about weak acids? Is there a leveling effect for weak acids? Are all weak acids the same strength in water? And it turns out no, there's no leveling effect for weak acids. The stronger the weak acid, the easier it is to pluck the proton off, or the easier it is to donate that proton. And so the stronger the weak acid, the more hydronium, the weaker the weak acid, the less hydronium. All right, now we're going to switch here to this. Ammonia is a weak base. Is this an ionic compound? No, this is a molecular compound. But we know something about weak bases. Weak bases are weak electrolytes. Weak electrolytes do what? Weak electrolytes partially ionize, just like weak acids, are weak electrolytes, weak acids, partially ionized. The degree of ionization depends on how weak the weak acid is. The weaker the weak acid, the less it ionizes. And so if we look at ammonia, let's do the same thing. Ammonia is a weak base. What do weak bases do? Weak bases are weak electrolytes. Weak electrolytes partially ionize. And so what does ammonia ionize into? Well, a lot of people will say ammonia should ionize into H plus and NH2 minus. H plus and NH2 minus. That's what it ionizes into. Is that correct? No, this is not correct. In fact, you might have seen NH2 minus before. NH2 minus, you might have seen it here. NH2 minus is called amide. And actually amide is in the strong base category. Do you know the strong bases? You said there's 7 strong acids, right? How many strong bases are there? A lot of people, when I ask this, they say sodium hydroxide. Okay, 1. What else? Potassium hydroxide, 2. Lithium, cesium. How about magnesium hydroxide? Strong base? Yeah? All right, so you know magnesium hydroxide, you know what they use it for? They use it in milk of magnesia. Milk of magnesia, people drink that in case their stomach is too acidic. It neutralizes some of the stomach acid, right? So you drink your milk of magnesia. Let's say I ran out of magnesium hydroxide milk of magnesia. Can I substitute sodium hydroxide for that? Because most people will have milk of magnesia, maybe not most people, some people will have milk of magnesia in the house, which is for antacid. And some people will have sodium hydroxide, which is a lye or drain cleaner. And so if you ran out of magnesium hydroxide, could you substitute the sodium hydroxide for that? So, you know, would you recommend your friend, I ran out of the milk of magnesia, take some sodium hydroxide drain cleaner instead. It'll neutralize some of your stomach acid. No, why not? Both are metal hydroxides, right? Are both strong bases? No? Then what are the strong bases? Is magnesium hydroxide a strong base? No, it's not considered a strong base. Do you know what the pattern is? Have you recognized the pattern? The pattern is pretty simple. The strong bases are group 1, calcium, strontium, and barium hydroxide. What's special about group 1, calcium, strontium, barium hydroxide? Those are what we call the soluble hydroxides. All other hydroxides are insoluble. And so the reason why milk of magnesia doesn't kill you like drain cleaner would kill you is because it's an insoluble hydroxide, whereas sodium hydroxide is a soluble hydroxide. And so we have the hydroxides here, we have the soluble hydroxides, but the hydroxides aren't the most powerful base. There are more powerful bases than hydroxides. What are they? Amide is one. Amide is a very powerful base, more powerful than hydroxide. For all these powerful bases, sulfide, amide, oxide, hydride, methide, all these powerful bases will ionize 100%? No. Bases do not ionize. You know, acids is okay. We can say acids ionize or hydrolyze. For bases, we never say the base will ionize. Instead, what we say is that the base will Instead, what we'll say is that the base This doesn't make sense, does it? Because if we say the weak base ammonia ionizes into the strong acid, H+, and the strong base, amide, does that make sense? So we're going to form a powerful acid and a powerful base. It doesn't make sense. Instead, bases do not ionize. Bases hydrolyze. Now, what does hydrolyze mean? Hydrolyze just means it reacts with water, just like we saw before. And so when a base hydrolyzes, well, ammonia is the base. Bases are proton acceptors. Water can go either way. It's amphoteric. And so if ammonia is the base, water will act as the acid. And so what forms here when ammonia and water react? NH4 plus and OH minus. NH4 plus and OH minus. It's weak, so most of it stays as NH3 and water. This is the same thing. You know, weak acids will partially hydrolyze. So if I have acetic acid and water, this is going to form some hydronium. It doesn't form, this reaction doesn't go 100%, so it just forms a little bit of hydronium and a little bit of acetate. And so there are different ways we could show that. One way we could show that is drawing a big arrow reversed. And in fact, it's 99.9% unreacted molecules, only 0.1% reacts in this hydrolysis reaction. And the same thing goes for ammonia and water. It's pretty much 99.9% ammonia and water, and only about 0.1% of the ions here. But even at 0.1%, this could be high enough concentration to react. And so if we have ammonia and water, we have to think about the potential for ion combinations. And the ion combinations, when we have ammonia and water, would involve ammonium. Well, ammonium is not very reactive because the group 1 and ammonium salts are totally soluble. It's the hydroxide. Hydroxide could form good favorable ion combinations with other species here.